In our previous presentation, we understood through an example how the algorithm works. We learned that the algorithm works correctly and it solves the problem of Towers of Hanoi. We did the implementation of Towers of Hanoi in the previous lecture. Now, in this lecture, we will learn how to write the recurrence relation of moves of Towers of Hanoi. Eventually, we want the recurrence relation because we want to know the number of moves required to solve the problem. If we have, let's say, n disks, then how many moves do we need in order to transfer n disks from one peg to the other? So we are interested in knowing the number of moves, and we can get the number of moves from the recurrence relation of moves. That is why it is important to write the recurrence relation of moves of Towers of Hanoi from the algorithm. So we are ready for this lecture. Let's get started and let's see what are the topics. The topic of this lecture is Towers of Hanoi, recurrence relation of moves. So let's proceed and let's understand how to write the recurrence relation of moves of Towers of Hanoi from the algorithm. We saw this algorithm in our previous lectures. We know this algorithm has the capability to solve the problem of Towers of Hanoi, that is, to transfer the disks from one peg to the other. Now, from this algorithm, we can write the recurrence relation of moves, and from the recurrence relation of moves, by applying the substitution method, we can easily obtain the formula to calculate the number of moves when there are n disks. Here we know that this algorithm has the capability to transfer n disks from peg A to peg B via peg C. Now, we are ready to write the recurrence relation of moves for this algorithm. This time we are not interested in writing the recurrence relation of time, but the recurrence relation of moves. So let us assume m of n represents the number of moves in Towers of Hanoi. We used to represent time with t. We are representing moves with m. So that is why we have m here. So this is m of n. The input is n, which is representing the number of disks. Now let's write the recurrence relation of moves for this algorithm. Here first we need to observe the base case. In the base case, we can observe that if n is equal to 1, then we need to perform just one move. So it is clear that if we have just one disk, that is if n is equal to 1, then m of n must be equal to 1. What about the recursive case? In the recursive case, we have TOH of A, C, B, n minus 1. Then we have move A to B. And then we have TOH of C, B, A, n minus 1. Here we are calling TOH twice. And also we can observe that we have n minus 1 in both the cases. So one thing is clear, that in case of the recursive case, we will have 2 times m of n minus 1. If m of n is representing TOH of A, B, C, n, then it is clear that m of n minus 1 is representing TOH of A, C, B, n minus 1 and TOH of C, B, A, n minus 1. We are not interested in the order of these pegs. We are only interested in the number of disks we have here. If we have n disks here, we have n minus 1 disks in these two cases. So it is clear that m of n must be equal to 2 times m of n minus 1 plus 1. Why plus 1? Because we are performing one move here. So the recurrence relation is clear. It is m of n equal to 2 times m of n minus 1 plus 1 if n is greater than 1. If there are more than 1 disks, then this must be the recurrence relation. Otherwise, if n is equal to 1, then m of n must be equal to 1. There will be only one move if there is just one disk. So this is the recurrence relation of moves of Towers of Hanoi. Now we are fully ready to solve this recurrence relation using the substitution method so that we would be able to obtain the formula to calculate the number of moves from the number of disks. So now let's do this. Now we are going to solve this recurrence relation using the substitution method. Let's apply the substitution method. We need to start from the recursive case, that is mn equal to 2 times m of n minus 1 plus 1. So this is the recursive case. Now we know that m of n minus 1 can be replaced or substituted by 2 times m of n minus 2 plus 1. Here we can replace n by n minus 1. We will get 2 times m of n minus 2 plus 1. So clearly we can replace m of n minus 1 by 2 times m of n minus 2 plus 1. This is what we will get after the replacement. Here now we have 2 times m of n minus 1 plus 1. M of n minus 1 is replaced by 2 times m of n minus 2 plus 1. Now we can open these brackets and multiply 2 by these terms of this expression. If we multiply 2 by this term, we will get 2 square times m of n minus 2. And if we multiply 2 by 1, we will get 2 here. So eventually we are getting 2 square times m of n minus 2 plus 2 plus 1. This is new m of n in terms of m of n minus 2. Now what's next? We can similarly substitute m of n minus 2 by 2 times m of n minus 3 plus 1. How it is the case? Here we are replacing n by n minus 2. We will get 2 times m of n minus 3 plus 1. So let's replace m of n minus 2 by 2 times m of n minus 3 plus 1. The rest of the expression can be written as it is. Now here we need to multiply 2 square by this term and this term. We will get 2 cube times m of n minus 3 plus 2 square. So this is the expression so obtained. 2 cube times m of n minus 3 plus 2 square plus 2 plus 1. Now the pattern is quite clear. We can continue in the same way up to, let's say, m of n minus k. We know if we have 3 here, then we will have 3 here. If we have 2 here, then we will have 2 here. If we have 1 here, then we will have 1 here to the power of 2. So it is clear that if we have m of n minus k, then we will have 2 power k here. And we can observe the powers are reducing by 1 after this. So after 2 power k m of n minus k, we will have 2 power k minus 1, 2 power k minus 2, and so on up to 2 square plus 2 plus 1. So we will have this m of n, which is equal to 2 power k times m of n minus k plus 2 power k minus 1 plus 2 power k minus 2 up to 2 square plus 2 plus 1. Here I am assuming that m of n minus k has reached the base case. This means that n minus k is equal to 1. In place of n, we must have 1. So here we have n minus k equal to 1. This is my assumption. I am assuming that we have reached the base case. Therefore, n must be replaced by n minus k, and n minus k is equal to 1. If n minus k is equal to 1, then we can easily find the value of k in terms of n. K will be equal to n minus 1. Now we can replace n minus k by 1. This is what we have assumed. What is m of 1? M of 1 is equal to 1. So we can replace this by 1. We will get 2 power k times 1, which is equal to 2 power k. Now we have this summation. 2 power k plus 2 power k minus 1 plus 2 power k minus 2 and so on up to 2 plus 1. We can say this is sum of GP. If it is not properly visible, then we can rearrange this summation like this. I have placed 1 first, then 2 and then 2 square, and at the end I have placed 2 power k. This is the same summation but now rearranged. This is the sum of GP. We can observe that each term is obtained after multiplying the previous term by 2. This means the common ratio is 2 and the first term is 1. What about the number of terms? We have a total of k plus 1 terms. Observe we have 2 power 0 here. The summation is starting from 2 power 0, not 2 power 1. So it is clear that there are a total of k plus 1 terms. If we apply the formula of sum of GP, then it is equal to a times r power n minus 1 divided by r minus 1. A is multiplied to the fraction. A represents the first term, r represents the common ratio, and n represents the number of terms. So what we will get? We know a is 1, so a will be replaced by 1. we'll be left with fraction only, which is r power n minus 1 divided by r minus 1. Now what is r? We know the common ratio is 2. So it is clear that r needs to be replaced by 2. In the denominator, we will have 2 minus 1. 2 minus 1 is equal to 1. So we will left with nothing in the denominator. Only the numerator term is what we are left with. In the numerator, we have 2 power k plus 1 minus 1. Because n will be replaced by k plus 1 and r will be replaced by 2. So we will get 2 power k plus 1 minus 1 like this. Now we can replace k by n minus 1 easily. After replacing k by n minus 1, we will get 2 power n minus 1 plus 1 and then minus 1. Now what is n minus 1 plus 1? It is equal to n only because minus 1 plus 1 is 0. So we will left with 2 power n minus 1. So these are the number of moves I was talking about. So if there are n disks, then we will have 2 power n minus 1 moves. So it is clear that m of n is 2 power n minus 1. And we can observe the moves are exponential. If there are n disks, then we have 2 power n here. So for small number of disks, we'll get exponential number of moves. Let's take some examples. Let us assume n is equal to 1. If n is equal to 1, then by putting n equal to 1 in the formula, we will get 2 power 1 minus 1. This is equivalent to 2 minus 1, which is equivalent to 1. So m of 1 is equal to 1. And this is correct as well. We know that if n is equal to 1, that is if we have just one disk, then we need just one move. The base case itself is satisfied. So m of 1 is equal to 1. What if we have two disks? We learned that if we have two disks, then we need 3 moves. Let's see whether we are getting the correct answer or not. By replacing n by 2, we will get 2 power 2, which is equal to 4. And 4 minus 1 is 3. So it is clear that m of 2 is 3 and we are getting the correct answer. What if we replace n by 3? We also learned this, that if we have 3 disks, then we will get 7 moves. Now let's see whether we are getting 7 or not. If we replace n by 3, we will get 8 here and 8 minus 1 is 7. So it is clear m of 3 is 7. We are getting the correct answers for the number of moves. It is clear the formula is correct. It is 2 power n minus 1. Now let's say that n is equal to 10. What if we have 10 disks? Then how many moves do we need to solve the problem? If n is equal to 10, then this is 2 power 10. 2 power 10 is 1024. And 1024 minus 1 is 1023. So these many moves we need to solve the problem. We have quite a lot of moves right now for just 10 disks. Now what happens if we have 30 disks? How many moves do you think it will take? If we have 30 disks, then the number of moves will be 1073741823. It is quite a large number. It is nearly 1 billion. 1 billion. Can you imagine? These many moves we need in order to solve the problem of Towers of Hanoi with 30 disks. Just imagine the number of moves at this point. It is so huge. If one move takes 1 second, then it will take 1 billion seconds to transfer 30 disks from one peg to the other without violating any rule of Towers of Hanoi. Then you can imagine that 1 billion seconds is how much? It is nearly 32 years. 32 years. This is the reason why this Towers of Hanoi puzzle is so popular. It is one of those problems which takes exponential amount of time to solve the problem. Here we are assuming if one move takes 1 second, then in order to solve the problem of Towers of Hanoi with 30 disks, it will take nearly 32 years. Now what if we have 60 disks? We can imagine it will take forever to solve the problem. So, this is the problem of Towers of Hanoi, and we also got the formula to calculate the number of moves. This is what we need to remember. The number of moves is 2 power n minus 1. And we got this formula by solving this recurrence relation through the substitution method. So we are done with this topic, towers of Hanoi, recurrence relation of moves, and this means we are done with this lecture as well. Okay friends, this is it for now. Thank you for watching this presentation. I'll see you in the next one.